In example 6, we're going to use function notation to find the following values. In part A, we are looking for f of 2. So what we need to do is we need to plug in 2 into the original function f of x for each of the x values. So we're going to plug it in for every single x value that we see. For part A, we first have to write f of 2 is equal to, then I'm going to plug in the 2, but remembering to use parentheses when we plug in the value of 2. Okay, so we're going to start from left to right. Negative 2 squared is negative 4 plus 5 times 2, that's positive 10, minus 3. We're going to continue to simplify. Negative 4 plus 10, that's 6, minus 3. And finally, 6 minus 3 yields 3. In part B, we're not plugging in a number, we're plugging in a letter for the function f of x. So we'll write first f of q is equal to negative q squared plus 5q minus 3. Again, we use parentheses around each of the values that we're substituting into the equation. So we have negative q squared, which simplifies to negative q squared. 5 times q is just 5q, and we have negative 3 here. Since we cannot collect like terms, that is it for part B. F of x was equal to 2x plus 3. What I want to do is I want to plug in the entire value a plus 1 into the x. So we'll write first g of a plus 1 is equal to 2 times the quantity a plus 1 plus 3. Now we need to simplify by distributing the 2. So I have 2a plus 2 plus 3. We're going to collect like terms. So we have 2a plus 5. Example 7. For each function, find f of 3. So in part A, we want to plug in the 3 for the x. So we'll write f of 3 is equal to 3 times 3 minus 7. Again, we're substituting the 3 for the x value. 3 times 3 simplifies to 9. And 9 minus 7 is 2. In B, we have a function that is defined as a set of points. Now remember, the 3 represents the input. So the question is asking, what's the output if we plug in 3? So we know that 3 is the input, so the output must be 1. The output, remember, is the y coordinate. So f of 3 is equal to 1. For part C, we know the input is 3 and the output is 5. So f of 3 is just 5. In part D, we have to figure out when the input is 3 and determine the output. So remember, the input is associated with the x coordinate. So in this case, we have the point 3, 4 lies on the graph. So 3 must be the input and 4 must be the output. So f of 3 has to be equal to 4. So essentially for part A, we have this situation where the function value f of x of 1 and f of x2 has a situation where f of x1 is less than f of x2. So our function is increasing as we move from left to right. In B, the function decreases if whenever x1 is less than x2, the function value is greater on the left than it is on the right. So here we have f of x1 is higher than f of x2. That would be a case where the function is decreasing. As you go from left to right, the function goes from high to low. In C, we have f as a constant function if whenever we have x1 and x2, the function values are the same. So in this case, we have a horizontal line where f of x1 is the same height as f of x2. There's no change in the height as we go from left to right. It's a constant value. Example 9. Determining intervals over which a function is increasing, decreasing, or constant. So we have a function here. And I'm going to start from left to right. Looking from left to right, we see that it decreases down to this vertex at -2, -1. So this function decreases from -infinity to -2. Notice that we're using open intervals because the direction wants us to use open intervals. If I look at the function where it's going from left to right again, it's starting to increase from -2 to 1. And in order to figure out what values to use, I'm looking at the x coordinates. So in this case, it goes to -2 on the left side of the function when it starts increasing, and it stops at 1. So the increase is from -2 to 1. And it's going to be constant from 1 to infinity. Again, we're using open intervals because the directions want us to use open intervals. Example 10. The figure shows the relationship between the number of gallons, g of t, of water in a small swimming pool and time in hours, t. By looking at this graph of the function, we can answer the questions about the level in the pool at various times. For example, at time 0, the pool is empty. The water level then increases, stays constant for a while, decreases, then becomes constant again. Use the graph to respond to the following. So let's look at the first question. What is the maximum number of gallons of water in the pool? When is the maximum water level first reached? So let's look at the graph. the highest value that I can see for the output is 3,000 gallons. And that's first reached when the time is 25 hours. Notice that the water level increases from 0 to 25 hours. So it's increasing from 0 to 25 hours. It's going to be constant at 25 to 50 hours. And is also constant at 75 to 100 hours. It is decreasing from 50 to 75 hours. From here to here it's decreasing, so that's from 50 to 75 hours. How many gallons of water are in the pool after 90 hours? According to the graph, we have 2,000 gallons after 90 hours. Part D. Describe a series of events that could account for the level changes shown in the graph. We notice that there's a steady increase from 0 to 25, and the height of the pool is constant at 3,000 gallons. A possible scenario would be the pool filling up and staying constant. After that, we have that the pool water starts to decrease, possibly because of people entering the pool and splashing out the water, and that could account for this decrease. Afterwards, we take another measurement and it's constant again because the pool hasn't been refilled.